Hello, everybody. This is, we're going to call this one the tower problem. So what we've got is a tall, thin tower right here. And the crosshatches are just support struts. Um, where it contacts the ground, there's a ball joint, ball and socket joint. So there's flexibility. This type of joint, as you remember, provides reaction forces, but it can't provide a moment. So it'll allow this thing to sway a little bit, and it'll allow it some motion. Um, so let's put this in a coordinate system. So here you see it lined up. It's the tower's in blue here. It's lined up. It is on the y-axis. And we arranged the XZ plane so that one of the three support wires holding it up, is along the x-axis. That's this BC, okay, is along the x-axis, just to make things a little bit easier. And then we have two other wires, BE and BD. The dimensions are on here. The 20 meters here that I'm highlighting is the x distance in the xz plane, from the z-axis to the point D. The 50 meters is from the x-axis to point D. 40 meters here along the z-axis to point E, and 40 meters here parallel to the x-axis from point E to the z-axis. Okay, so what other information are we given? Well, here we're given. We've got a stray mark there. We're given that there's equal tension in each cable. So there's 2 kilonewtons of tension in each cable. We're asked to find the reactions at the ground at point A. And we assume the tower is massless. So the only forces acting on it are the 3 cables. Okay, so our next step, as always, is our free body diagram. So the cables have been replaced by 3 force vectors. The ground has been replaced at point A by 3 reaction forces, 1 along each of the major axes. And the tower itself is massless. We're just replacing it by a line along the y-axis. So what we're going to need are unit vectors. BC is easy because that's, let's see, well, we still need that because it's along the x-axis, a little easier, but we still need a unit vector because it's not right on the axis. So let's start with BD. Okay, the vector BD is 2I minus 70J plus 50K. The unit vector for BD is over the magnitude of BD, and so magnitude BD, I'll let you do this out if you want to. I'll just give it to you, 88.32. So that when we put this all together, we get a unit vector along BD of 0.226I minus 0.793J plus 0.566K. All right, that's one of our unit vectors, BD. Now for BE, we have of 40. Let's see. I'm just checking something here. Yeah, I made a mistake over here. This is 20, not 2. So 20. Unit vector BD is 20 along the x-axis, yeah. Okay. And BE is 40I minus 70J minus 40K. Okay, that's the vector. The unit vector is that vector divided by that vector's magnitude. So the magnitude is the square root of the sum of the squares, which for this one comes out to about 90. So the unit vector, after we go through the algebra, ends up being 0.444I minus 0.778J minus 0.444K. And our last one, vector BC, a little bit easier, but still has two components, minus 50I minus 70J plus 0K. The unit vector is going to equal that vector over the magnitude of that vector. Magnitude of BC is the square root of the sum of the squares, which is 86.02. And so we get a unit vector for BC of minus 0.58I minus 0.814J. All right, we have our unit vectors. So now the force vectors themselves are just the magnitude times the unit vector. So let's put those, write those clearly. So the vector FBD, the force vector FBD, is going to equal 2.0 kilonewtons times its unit vector, all right, so that gives us 0 in kilonewtons, 0.452I minus 1.586J plus 1.132K. And this is all in kilonewtons. Force BE is, again, all the forces were 2 kilonewtons, and that's just multiplied by the unit vector for BE, which was minus 0.581I minus 0.814J plus 0K. And when you multiply that out, you get minus 1.162I minus 1.162J no 1.628J plus 0K, and this is in kilonewtons. And the last one, force BC is 2 times, actually, I did these backwards, didn't I? Yep. So this is BC. Okay. So I'll do BE here. Good thing that the forces are all the same magnitude. Okay, so the unit vector for BE is 0.444I minus 0.778J minus 0.444K. And this comes out to 0.888I minus 1.556J minus 0.888K, and that's all in kilonewtons. Okay, so we were asked to find the reaction forces at X, Y, and Z. So the reaction force at X, reaction force in X direction at A equals the sum of the X components of F BD, F BC, and F BE. Okay, so what does that look like? So AX is going to equal the sum of the I components of those three vectors. 4, 5, 2 plus, so plus 8.888 minus 1.162, and that's minus 0.1178 kilonewtons. The reaction force at Y is going to be the sum of the Y components of those vectors, minus 1.586 minus 1.556 minus 1.628, and that yields minus 4.77 kilonewtons in the Y direction. And in the Z direction, you have 1.132 minus 0.888 plus the third force has a 0 component in the Z direction. So this comes out to 0.244 kilonewtons. Okay, so those are your reaction forces for this tower that has a ball and socket joint and it cannot supply a moment and is simply reacting, supplies a reaction force in each of the three directions. Now, we're going to take that same problem, okay, and now assume the tower is bolted down to a concrete platform. Okay, so now, not only do you have reaction forces, but now it's restrained such that it supplies a moment. Okay, so it's going to resist rotation. So in this case, forces are the same. Okay, so we don't have to redo that. But what we do need is we need the moment at A. All right, so remember, moment about a point is the position vector, let's say for AB. Well, I'm going to have a position across the face. Now, this problem has a simplification, because if you use RAB as position vector, it works for all three forces, because all three forces line of action intersects with position vector AB. So you only have to find one position vector. And RAB is a particularly easy position vector. It's just 70J, because it's coincident with the y-axis. So you can do this two ways. You can do R cross F for each force, or as I did in a previous problem, you can do R cross the sum of F, which is, I think, easier because you end up only doing one matrix. So let's rewrite for our particular problem. The sum of the moments about A is going to equal RAB, our position vector, crossed with the sum of the forces vector. All right, and the sum of the forces vector is force BD plus force BE plus force BC. So all we're going to do, I'm going to skip this step because you can do this. All you're doing is you're adding the x components, adding the y components, adding the z components of these three vectors, and that leaves you with the summation vector is 0.178i minus 4.77j plus 0.244k. All right, so we have our position vector, we have our force vector. Now we can calculate the moment. So the moment about A, RAB cross the sum of the forces is, let's set this up, I, J, K. So this is 0.70, 0.178. Looks like a negative sign there. 0.178 minus 4.77, 0.244. All right, we work that out. So this equals, for our I direction, we have just 70 times 0.244. Then for our j direction, we have 0. And for our k direction, we get k direction is minus 70 times 0.178. So the moment about A equals 17I minus 12.5K kilonewton meters. Now, so that's the moment about A. Therefore, the reaction moment at A must be equal and opposite. Okay, so that M is going to equal minus 17.1 I plus 12.5 K. All right, now, so that completes the answer to this version of the problem because the forces were the same. But what this does tell you is, look, with those original forces, the tower was unstable because there was this unbalanced moment. So if in the first case with that ball and socket joint, that tower in that situation would have twisted. All right, so it was an unstable situation. So the original problem was unstable because there was an unbalanced moment and the support at the bottom could not generate a reaction moment. In the second version of the problem, bolted to the concrete pad, so that can generate a reaction moment, so that's a stable situation. It just has to generate this level of moment. All right, so how would you fix that first situation if you really want to have that ball and socket thing? Well, you have to rearrange your guy lines, the positioning of those wires. You're going to need to change their placement, and ideally, if you could perfectly symmetrically place them, like if you're going to use 3 lines, you'd have to put them 120 degrees apart and exactly the same distance from the point, from the top of the tower on a perfectly flat surface, perfectly flat ground, and that should give you sum of forces, sum of the moments being 0. All right, so hope that helped, and that's it for this one. See you later.